In this video, I'd like to discuss the basics of power supply rejection ratio, or PSRR for short, what it is, what it means, and why we need to understand it to design better circuits. The main focus of this video after that will be using this LDO test PCB that I had manufactured by JLCPCB to measure the real-world power supply rejection ratio of this board's LDO low dropout linear regulator in combination with the surrounding circuitry. And I'll show you some various measurement techniques, what to pay attention to, and we'll look at both the frequency as well as the time domain. A huge thank you to JLCPCB for sponsoring this video. I had these LDO test PCBs manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. At the time of making this video, JLCPCB is offering their layout service, which is a professional PCB design solution that transforms your schematic into a ready for manufacturing PCB layout. It's the ideal choice for individuals who have a schematic but lack the time or interest to design the PCB. Engineering teams that want to focus on product development and leave layout to the experts, anyone looking for a fast, reliable, and time-saving one-stop solution, and as a user, all you need to do is submit your schematic and requirement form. JLCPCB's team of professional engineers will handle the layout and routing and work with you to ensure the design meets your PCB requirements. JLCPCB's layout service is made possible by a skilled engineering team with experience in high-speed, high-density, and multi-layer designs. There's seamless integration with JLCPCB's PCB manufacturing and assembly services, and of course full confidentiality for all of your projects. I'd strongly suggest checking out JLCPCB and their services. Links will be in the description box below. And as usual, JLCPCB has many coupons that you can use for various types of orders. Links in the description box below. Before we move over to doing measurements on real-world test PCBs and devices, let's briefly go over power supply rejection ratio basics and why power supply rejection ratio, or PSRR for short, is important to know about. The image in the top left illustrates the basic example. Let's say we have some sort of regulator, some sort of power conversion device. This could be a switching regulator, it could be a simple linear low dropout regulator, where we initially want to have some sort of input DC voltage that is then stepped down to a lower output DC voltage that is also regulated, so a stable DC output voltage. In the real world, however, we pretty much never have a clean input DC voltage source. The input DC voltage will be superimposed. On top of that voltage, we'll have some sort of AC noise, AC ripple. And this is illustrated in the waveform above. Our mean DC value is indicated by the dashed line, but on the top of that, we might have some sort of sinusoidal ripple, just for the sake of simplification. The regulator itself is a control loop and will be able, in certain frequency bands, at certain frequencies and certain amplitudes, to be able to attenuate this input AC ripple and provide a somewhat cleaner output waveform. Now, the output waveform, in theory, should be DC, but in practice it is not. So the output voltage waveform will also have a DC component, which is the main component we're interested in, but it might have some small amount of AC noise signal or AC ripple, and that's illustrated again in the waveform above. We have an average DC output, indicated by the dashed line, but most likely a smaller ripple amplitude, but similar ripple characteristics to what we saw at the input signal that feeds the regulator. The question is, how well does that regulator attenuate the input noise and just give you a clean DC output? Or in other words, how much noise from the input, this AC noise, couples to the output? And that is the basic idea behind the power supply rejection ratio, or PSRR. It is the ratio between the output voltage noise divided by the input voltage noise, or AC ripple out divided by AC ripple in. Note sometimes that the power supply rejection ratio is defined the other way around, so the V in ripple divided by the V out ripple. In decibels, we just simply take the base 10 logarithm multiplied by 20. Now, ideally, of course, you want a power supply rejection ratio of 0 or minus infinite dB if defined in the way shown here. For any input signal, regardless if it's pure DC or it has some AC noise and various frequency components, we want the regulator at the output to have a pure, clean DC output signal with no AC components. That's our theoretical ideal. However, of course, this is not achievable in practice, and that is why we choose certain regulators which have particular PSRRs in certain frequency bands, depending on the circuit we're designing for. The PSRR itself depends on many factors. It depends on the regulator you choose, so different regulators will have different PSRR characteristics across different frequencies. It depends on the regulator type, if you use a switching, if you use an LDO, depending on the control loop around it. It depends on the surrounding circuitry, what type of capacitors you have, and also the operating point. So what's your input DC voltage, what's your output DC voltage, what's your load, your current draw, and much, much more. So it isn't just a simple single number. Again, PSRR is particularly important for low noise sensitive circuits. For instance, if you have a noisy input voltage feeding a regulator, let's say you have 50 or 60 Hz mains component in that DC input, and the regulator has terribly poor power supply rejection ratio around those frequencies, that 50-60 Hz will be in some way, shape or form coupled to the output. Now, if that feeds an analog supply rail, for instance for some sensitive audio circuitry, which is in the range typically of 20 to 20 kHz band, that isn't particularly great news. Also, noise coupling onto your DC rails can worsen the performance of digital circuits by introducing jitter, phase noise and oscillators and more. Performing a PSRR measurement is actually fairly straightforward. There are many different ways of doing this. On the right-hand side, again, we have our regulator where we want to measure its power supply rejection ratio. That means we want to feed in a DC voltage, but we want to superimpose an AC voltage on AC ripple. Then at the output, we have a certain DC voltage, which for the case of this, we aren't terribly interested in, but we're interested in the AC component that appears due to the AC input ripple. Then we measure the output AC ripple, we measure the input AC ripple, and divide the output AC ripple by the input AC ripple. And that's how we perform the PSRR measurement. The question is, how do we get this superposition of DC voltage and AC ripple, which is controlled by us or by the person doing the measurement? And one method, of course, might be that you have a fairly capable lab power supply where you can apply a DC voltage and internally in the power supply it can generate an AC signal. You might just have a simple function generator, which is of course typically heavily current limited, but for low power designs that might be sufficient. We have a function generator with a DC offset and a small AC signal superimposed on top. But what we're going to be doing in this video is using something known as a line injector, which basically does the superposition for us. It takes in a DC power supply. In our case, this will be a lab power supply, which provides the DC signal. We'll use an AC wavegen, which is there to produce the AC input ripple. The line injector then modulates the DC voltage by the AC voltage, and then we get our superposition. The line injector itself, the most simple form is some sort of transistor, some sort of pass element, where we feed in the DC voltage, and the gate of this pass element is modulated by the AC voltage. Therefore, then at the output, we simply have the superposition, the addition of the DC voltage and the AC voltage. This is a very, very simplified representation of something like a line injector, but what you're trying to do is just modulate the input DC voltage by an AC voltage. Now, of course, there are few potential issues depending on how complex you design your line injector, but for something as simple as just a series pass element transistor, you might have issues with nonlinearities, with maximum bandwidths, switching speeds, maximum input-output voltages, maximum gate voltages, maximum currents, and you will also typically have, for something like this, a resistive output impedance, and we'll see why that is an issue later on. In any case, we'll soon be starting to look at some measurements, and for our measurements we'll be using this custom LDO test board which contains a low dropout linear regulator U1. We have placements for various input capacitors, output capacitors, feedback networks, as well as various loads we can apply to the output for determined output currents, and this is a very simple test case that allows us to easily measure the power supply rejection ratio of this particular low dropout linear regulator. Now let's move over to performing real-world measurements in the frequency domain to try and figure out and measure the power supply rejection ratio of our LDO regulator. For this, initially, I'm going to be showing you how to do this with the Bode 100 vector network analyzer as pictured on the top on this image, where the output of the Bode 100 feeds our line injector's AC input signal, so that will apply this AC signal bias. Then the channel 1 input of the Bode 100 will connect to the input of the LDO regulator, and channel 2 will be connected to the output of the LDO regulator. So in this way, we can do a full gain phase transfer function measurement, the relationship between the output relative to the input, given our DC bias plus AC signal on top, we can figure out the ratio of AC signals of output to input, and that gives our power supply rejection ratio. I'm using 10x probes for channel 1 and channel 2, and the whole board, this LDO test board, is powered by a lab power supply. We can then later alter the input voltage to see what effect that has on the power supply rejection ratio, and I've also set up the LDO test board to sync 150 milliamps of current, which we'll see later on. The line injector connections are as follows. Again, from the Bode 100 output signal, just with the BNC coax cable, I'm feeding the input of my line injector. So this is my AC signal, and I have positive and negative terminals coming from my lab power supply. So that's my DC signal going into the line injector. Then the line injector output is simply a negative and positive terminal, and those are the terminals that then go to the LDO test board, and that's the DC plus AC superimposed signal. This is then the connections we have initially for our calibration. I've attached channel 1 to the input of our test board and channel 2 of the Bode 100 input also to the input of our Bode 100 test board. In In this way, we can then nullify or cancel out any imperfections or non-idealities of our cable and measurement setup, so we have a null output before we perform the actual PSRR measurement. So we need to calibrate our system before we can perform an accurate measurement. The DC input terminals to this LDO test board are taken, of course, from the line injector output. Keep in mind this image still shows C3 in place, but I actually have removed the input capacitor C3 for reasons that I'll share in just a bit. And I've also enabled my first MOSFET here with this resistor array bank, so this gives me 150 milliamp output sync current directly at the output. So this is our calibration test setup for now. So now in the Bode Analyzer suite, what we want to do is perform a new measurement, and in particular we want to do a gain phase measurement, a transfer function measurement. We can see the limits, we can apply the inputs and outputs, and the overall or rather basic measurement setup, which we're doing, which is exactly what we need in this case. So I'm going to select that measurement, and the first thing we have to do is of course the measurement setup. So I'm going to go to the top, transmission gain. I'm using 10x probes at my inputs, and I want the high impedance input set to this. Because the power supply rejection ratio measurement is typically a very low amplitude measurement, I need to reduce my attenuators. So I'm going to go have them both for channel 1 and channel 2 to be at 0 dB. My source level I'm going to keep at 0 dBm for now, and we can see if we need to adjust that lower or keep it higher depending on how much noise or nonlinearity we have in the signal. My frequency sweep, I'm going to start at 10 Hz, but I'm going to end at 10 MHz. Number of points, I'm going to keep it 201 just for the sake of time, and a constant source level at 0 dBm as before. With the measurement setup in place, we want to perform a through calibration. So again, we're following this image with the two Bode 100 input probes, so channel 1 and channel 2 effectively shorted together. We have the line injector connected to the input, and the LDO is supplying 150 milliamps of current. So this is our baseline operating point, and we want to bias around this. Keep in mind, C3 is not populated because the output impedance of our line injector is actually resistive. So if we keep C3 populated, we actually have a low pass filter which will distort and alter our actual PSRR measurements. So the input capacitor, in this case C3, is typically depopulated in PSRR measurements. Now with all of this in place, what I'm going to do is I'm going to do a user range calibration, perform a new calibration, and simply click on start next to the through calibration. And this just makes sure we've nulled out our system. We have a pretty much flat 0 dB gain and 0 degrees of phase response with our input and output signals shorted. So that's performed now. Let's just double check by performing a single measurement and see if gain and phase are indeed flat and at 0 dB and 0 degrees. And that's exactly what we have. We have a flat line for the gain, and we have a flat line for the phase at 0 dB and 0 degrees of phase respectively. For the power supply rejection ratio measurement, we typically aren't that interested in the phase, so I'm going to hide that plot, which is trace 2, and we're just going to focus on our gain magnitude. With our calibration now in place, let's perform our first power supply rejection ratio measurement. For this, I've now just moved our channel 2 probe, which connects to the channel 2 input to the Bode 100. I've moved that from the input, where we did our through calibration, to the output like so. In terms of what we have placed on the board now, I have depopulated C3 as before, because again, the output impedance of the line injector is typically resistive, and we don't want that to form a low pass filter with the input capacitance, which would distort our PSRR measurements. So C3 is not placed. We have an input voltage of 9 volts nominal DC, which of course we superimpose an AC bias on top of. Our U1 regulates this for the most part, as we'll see, to 2.5 volts-ish DC, and we have an output capacitor currently C7 to 10 microfarads, which is an 0805 size multi-layer ceramic capacitor. What we then want to measure, or what we'll measure with the Bode 100, is the ratio of the AC output signal, or ripple, relative to the AC input signal, or ripple. Then that ratio of those two, so output AC to input AC, gives us the power supply rejection ratio. And of course we want a lower number for the power supply rejection ratio because we don't want any output AC ripple, theory and ideally given any input AC signal at any frequency, any amplitude. But of course that isn't possible, as we'll see. Now let's perform a single measurement. Again, our input voltage is 9 volts DC, our output voltage is 2.5 volts DC, 150 milliamps of current at the output. And now we have a plot of the power supply rejection ratio at this very specific operating point with this very specific regulator and with these very specific components around the regulator and of course the board design itself. We can see that the PSRR is given in dB, and for us now, of course, negative or more negative, a lower number is better, because that's the ratio of output to input signal. I want that to be a low number. As we can see, around DC or in the low frequency range, we have quite a bit of noise because this is a low amplitude measurement, a small signal measurement, and the power supply rejection ratio is seemingly very good, something around minus 80 dB in the band of about 10 to 1 kilohertz. Minus 80 dB, if we apply a 1 volt AC signal, theoretically, we would get only about 100 microvolts at the output, which is pretty good. However, as we go past 1 kHz approximately, we can see the power supply rejection ratio getting worse and worse. So for instance, already at around 10 or 20 kHz, we can see we've reached close to minus 30 dB of power supply rejection ratio. So suddenly for a 1 volt AC input signal, we might be getting something like 30-ish millivolts at the output. And as we go high in frequency, we also have some peaks and dips and notches at various places, but overall the trend of the power supply rejection ratio is upwards, and that is worse and worse. At about 4 MHz, we're already at minus 10 dB of power supply rejection ratio, and this is a typical trend for regulators, in that we have pretty good performance close to DC, and we get worse and worse as we increase in frequency. And this has a couple of reasons. One of them is, of course, the control loop of the regulator itself. Typically, control loop bandwidths are only in the order of kilohertz or tens of kilohertz. The bandwidth meaning the regulator can only react quickly to disturbances to the input voltage in that frequency band. Out of that frequency band, the negative feedback due to the reduction in open loop gain isn't as effective, and we let more AC input disturbances pass through to the output, and that's exactly what we're seeing here. So in the frequency range where the control loop is dominant and strong and quick, the negative feedback is great because it increases the power supply rejection ratio. Input signal disturbances are attenuated quite significantly. Also, these peaks and dips are due to, of course, the regulator itself, but also due to the surrounding circuitry. For example, input-output capacitors. Depending on the type of those capacitors are, the interconnects, you will get different peaks and dips. And this, of course, also depends lastly on the operating point, so our input voltage, output voltages, type of regulator, and so on. Let me save this measurement so we can compare it to other measurements we will be doing. I'll click on New Memory, give this a sensible name. And what we can do now is actually increase the input voltage to, let's say, 12 volts and see what effect that has on the power supply rejection ratio. I've now increased my input voltage, the DC input voltage, from 9 volts to 12 volts, and now let's perform another single measurement and compare it to our previous results with Vin of 9 volts DC. Now the red trace is our new curve with 12 volts DC input voltages, and as we can see, of course we have quite a bit of noise in this lower frequency region. We could of course play with the source level, make that shaped, but for now, for the sake of simplicity, I won't be doing that. But also in the higher frequency ranges with an altered input voltage magnitude, we can see the power supply rejection ratio has also changed. This could be due to derating of capacitors. It could be due to just changes of the overall system performance with a different input voltage. We might have better regulation in certain areas, but overall the trend is very, very similar. But keep in mind, your operating point does have an impact on the power supply rejection ratio. What I'd like to do next is to show you what happens if we, for example, alter the output capacitance. So I'm going to revert back my input DC voltage to 9 volts, but I'm going to place some different capacitances at the output and see what effect that has on the power supply rejection ratio. I've now adjusted the board, and now I've actually placed C5 with it, which is a 47 microfarad aluminium electrolytic, which is in parallel with our other output, with our previous output capacitor C7, again a 10 microfarad multilayer ceramic NO805 package. So let's see what that does now with the power supply rejection ratio. I've stored my previous two traces, so with a varying input voltage, but now of course we have this additional 47 microfarads aluminium electrolytic capacitor. Let's do a single measurement. And now the red trace is our new trace. Overall, the low frequency performance isn't terribly affected, and the high frequency performance isn't terribly affected either. But in the mid-band, where our aluminium electrolytic capacitor is effective, a fairly low impedance, that's typically around the 10 to 50 to 100 kilohertz range, and that's why we get a dampening and a slightly better power supply rejection performance around that band simply by adding more external capacitance to the output. So I hope that illustrates quite nicely how important the operating point is and the various parameters and external circuit components to the power supply rejection ratio and how to measure it. Keep in mind also the feedback compensation network. For example, if we were to add in C8 as well as our feed-forward capacitor, that will affect the performance of the power supply rejection ratio as well, because you're directly influencing the shape of the control loop gain by placing or not placing that capacitor and adjusting its values. Now that we've performed the frequency domain measurements, let's see what that means then for the time domain and where we can actually see the noise. And this might be slightly a bit more intuitive than the frequency domain measurements, and because you can actually see what is going on. And effectively, this time domain measurement is somewhat what's happening behind the scenes for the frequency domain measurement. What I have set up are the same connections as before. We have the line injector with a DC power signal from my lamp power supply, but the line injector now is being fed by the wave gen, which is part of my oscilloscope. Then I have channel 1 of my oscilloscope connected to the input, of the LDO test board and channel 2 of my oscilloscope connected to the output of this LDO test board. And that way I can apply an AC stimulus with a wavegen, I can monitor the input and monitor the output voltages. As we can see here, I currently have the wavegen off. My input signal is the yellow trace, my output signal is the blue trace, so then it's the DC plus AC input, DC plus AC output. Currently I have about 6 volts at the input, DC, and about 2.5 volts at the output due to the regulation of the LDO regulator. Now what I can do is of course apply a stimulus to the line injector and superimpose an AC signal using the line injector on my DC input. So currently I just have a 100 Hz sine wave at an amplitude of 1 volt, and this is of course AC coupled in the line injector. So if I click run, we can see now the input waveform, channel 1, the yellow trace, is the 6 volts DC plus a 1 volt amplitude AC sine wave. And because this sine wave is only at 100 Hz, we are still in the very good regime of the power supply rejection ratio. This was around minus 80 dB. That's why we're not getting too much noise out on the blue trace, which is our output of the LDO regulator. However, as we now increase the frequency, let's say from 100 Hz to 10 kHz, again a 1 volt amplitude sine wave, we can now see we have some noise on the output line, which is supposed to only be DC. But now we have this 100 kHz sine wave due to the imperfect power supply rejection ratio appearing at the output. And that's exactly what we're seeing here. And depending on your frequency, depending on the power supply rejection ratio performance of your LDO and your surrounding circuitry, you will get a different noise output for a certain noise input. And this can of course be crucial for your circuit designs. If you're trying to make a low noise analog design or an RF design, you have to keep this in mind. But hopefully that's a nice short visual demonstration of what's actually going on in the time domain. Thank you very much for watching this video. I hope it was useful and I hope it showed you the basics of power supply rejection ratio and how we can measure that both in the frequency domain and see what effect that has then on the time domain and why it's an incredibly important parameter for certain integrated circuits such as regulators or operational amplifiers, to name a few. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware, firmware, PCB design, and DSP videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.